Hi everybody, we continue with glycolysis in this video. Let me move a little bit myself again. Okay, yeah. And we're going to discuss two more reactions from phase one, aldolase, which we're about to do, and triose isomerase, and I will finish uh, the upper part of glycolysis. So what's the reaction? We made fructose 1,6-bisphosphate, so it's phosphorylated both ends, let's say, fructose. It's fructose from glucose because we moved the carbonyl. That's very important, so we can actually set up now the reaction we're about to talk to achieve cleavage um, of the carbon skeleton of glucose right in the middle between position 3 and 4 to give rise to two 3-carbon units, dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. The enzyme that catalyzes this reaction is called aldolase. It's a fully reversible reaction. Excuse me. And these are the products again. And this is really where lysis is put in glycolysis. This is where glucose is broken up. So, of course, that's a reaction that reactions that break carbon-carbon bonds. It fits into that group of reactions. And the carbonyl here is where we got it when we converted glucose 6-phosphate to fructose 6-phosphate, and it has a purpose, and this is the purpose here, to activate cleavage at this position close to it. How does that happen? The general mechanism is shown here. Here is a double bond between something electronegative, usually oxygen or nitrogen. In our case, they are oxygens, the X and Y. And the cleavage will be achieved in the following manner. Starting with this hydroxycarbon in our case, okay, the hydroxycarbon is gonna be converted to a ketocarbon, okay, so some general base will pick up the proton again, and then it's going to make the double bond here, so which will enable this bond to break, and the electrons have to go somewhere. The carbonyl is important to be there so it can receive them, so it serves as an electron sink in some way, and without it we wouldn't have cleavage. And then you go back in reverse. So we've seen this. We have this intermediate here with a double bond, and we have reformation. Okay. Now this became from a ketocarbon from a carbonyl carbon to a hydroxycarbon, but it will become again a carbonyl carbon shown here, and the double bond will pick up another proton and be done. So this is the business part that we are talking about. Okay, that was the Y in the previous scheme, and that was the X here, the oxygens. And I should say now, I mean, we have described how sugars exist in the cyclic forms, in the closed forms, and the open forms. Actually, the vast majority for any one of them, let's say in this case, fructose 1,6-bisphosphate, is the closed form, but there is always some that's in the open form, so there is an equilibrium. Under normal physiological conditions, it favors the formation of the closed form, and the way you go from open to closed is shown here. Okay, this hydroxycarbon this hydroxycarbon here, the oxygen on this hydroxycarbon will attack the carbonyl carbon of the sugar. The same thing happens when you have glucose, for example, and the carbonyl is at the very end. Okay, and that's how it's going to close, right? Simple as that. So I'm showing you in a little bit more detail here the mechanism of aldolase. Is actually a bit complicated, and the actual how is a little more complicated than we just described in the general scheme. And you have an amino group that forms first as an intermediate that participates in the formation of an intermediate. The amino group is from the actual enzyme, from aldolase itself. It is that one that will actually attack the carbonyl carbon first, okay, and open it up, and you move on. And actually what's going to happen is that the nitrogen will take the place of oxygen here, and you'll see how that happens and why it happens in this particular case. So the nitrogen of the amino group on aldolase attacks. You have a hydroxycarbon here now, You keep going, it becomes a full hydroxycarbon. Then, okay, you dehydrate this moiety here, and you end up with a CIF base. Okay, so why a CIF base? Because that's actually a better electron sink, as it turns out. Okay. Now, if you follow this textbook that is popular in biochem classes, somehow the mechanism starts from this CIF base, but you have no idea how we got to the CIF base, and this is the way it happens, right? Now we can actually follow the proper scheme, that the general scheme, the XYs that we saw earlier, okay? And now the reaction proceeds as follows. We have an aspartate on aldolase to subtract this proton from this hydroxycarbon, and then you break up the bond. Okay, so you generate right off the bat. Okay, so we generate the first product, which is glyceraldehyde 3-phosphate. So that's an aldehyde. Okay, there is a terminal carbonyl group right here. Okay, it is a sugar also. Okay, so this even though it's only 3 carbons, it's got an oxygen on every carbon, and one of which, so there's a hydroxy carbons, this one and this one. Of course, this one is phosphorylated because it needs to stay inside the cell, and the terminal carbon here is a carbonyl, so it's an aldose. Okay. Then what happens with the rest that stays there? This carbon will attack and will pick up the proton from the aspartate. Okay, and we have now we have to go back to make this to replace the nitrogen with oxygen. So we're going to hydrolyze the CIF base essentially, and water comes in, and you have a simple hydrolysis. Okay, the oxygen and water will attack the carbon of the CIF base here, and you open it up and keep going, and eventually, you know, when you form the carbonyl right here, now you reform the amino group on aldolase, and you are done. You got dihydroxyacetone phosphate, which is the second product. It's another 3-carbon sugar, and it's a ketose. Okay, it's not an aldose. Now, this is animal aldolases. In microbial aldolases, instead of the CIF base that is forming, and again, that's a key intermediate in aldolase formation in many organisms, including our own. But in many microbes, instead, there is some zinc bound to aldolase that serves the same purpose as an electron sink. And how can you tell them apart? Well, if you subtract, you can remove zinc, and with a chelating agent like DTA or something like this, and then this one would be unaffected, but this one would be inhibited, obviously, because it absolutely needs the zinc to do its job as an electron sink. Okay. So why did we do this? Well, these are key building blocks. Okay, they can be used to make lipids. Okay, so the Y in glycolysis, they fall in general in two, three reasons. So the glycolysis, on one hand, makes ATP. Okay, makes the 2 molecules of ATP, not in these reactions, but in the lower part of glycolysis that we'll discuss. But also glycolysis provides key intermediates for biosynthesis, especially these 3 carbon units. They're absolutely essential to make many lipids, for example. Aldolase is an important enzyme to regulate glycolysis. In fact, in some neurons, I believe, aldolase sits on the cytoskeleton and can be locally activated at that point and provide and activate glycolysis overall and provide the ATP necessary for cellular function. Okay, so that's that's about aldolase. What about the next enzyme now in the glycolytic pathway, triose-phosphate isomerase? As I said, some dihydroxyacetone phosphate can be used, let's say, as a building block directly. But let's say you don't want to use it as a building block and you want to push it down the rest of the pathway in glycolysis to make pyruvate, well, all you have to do is just convert it to glyceraldehyde 3-phosphate. So, and it's an isomerization reaction. And all you do is you're going to move this carbonyl from this position to the top position. And I think we've seen this before, and we'll see the mechanism in a minute. It has a special interest for enzymologists. It's an extremely efficient catalyst. It operates at near diffusion limit. Basically, it will do it as quickly as it can grab onto these things through diffusion that reaches the enzyme. It is similar to phosphoglucose isomerase when we isomerize glucose to fructose. Okay, it's exactly the same thing. Why? So we're not going to deal with it again. The why here is that equalizes all glucose carbons. So whether you are 1, 2, 3, that's equivalent now to 4, 5, and 6 in glycolysis. And so it's a flexible supply of 3 carbon units, interconvertible 3 carbon units. The reaction, again, as I said, is it will proceed through an NADO intermediate in exactly the same manner that we saw for phosphoglucose isomerase. So again, so you're going to have a double bond. The carbonyl will open up, and you have 2 hydroxycarbons. Again, it's an internal redox reaction, and then you do everything in reverse. But what's important here is that if you let it go on its own, you will get methyl glyoxal. So these 2 hydroxycarbons will become carbonyls, and that's a poison. It will cross-link everything in the cell. Okay, and so highly reactive poison. But TPI will do it so fast that there is no chance for methyl glyoxal, the poison, to accumulate. So there's actually a reason why it needs to be so super efficient and operates at the diffusion limit, this enzyme, right? But as I said, the next is going to be in reverse from what we saw, similar to what we saw. So now we are going to make the keto, the carbonyl at this position. We're going to form it here, open up the double bond, and gain a proton, and we are finished. So we got, again, from ketose here to an aldose in this case. So we had seen the same thing, but in reverse in phosphoglucose isomerase. So where we got from an aldose to a ketose, but these are fully reversible reactions. Okay, they can go back and forth. And with this, we concluded the upper part of glycolysis, which is phase 1 in our scheme here. And again, we got something useful. We got the 3 carbon units, which are used not only for glycolysis for the lower part, but also for biosynthetic purposes as building blocks. But importantly, we actually used ATP. We didn't make any. We spent 2 molecules of ATP for 1 molecule of glucose to get to this point. So now it's time to move on to the next phases. In the next videos, we'll see what happens to glyceraldehyde 3-phosphate that now can be fed straight into those pathways. All right, so we're going to stop here.